Welcome to Maths with EJD. In this video, I'll be talking about the Nash equilibrium, which is very popular and central to the whole idea of game theory. So let's start with the definition of the Nash equilibrium. Definition of Nash equilibrium. Okay, so a Nash equilibrium. In the previous video, we had done a bit of introduction to it. So a Nash equilibrium is a situation. It is a situation in a strategic game where no player can improve their payoff by unilaterally changing their strategy given the strategies chosen by the other players. So it's some kind of optimal solution in a game, so to speak. So let's look at some key points of this concept. Key points. So, first of all, each player's strategy is optimal. You can't improve on it. It's optimal given the strategies of others. Then, in a Nash equilibrium, no player has an incentive to deviate. Okay, then there can be one, multiple, or no Nash equilibrium. One, multiple, or no Nash equilibria in a game. So it's possible that in a game, you have only one Nash equilibrium. In some, you can have two Nash equilibria or more. And in some cases, you can even have no equilibrium at all, meaning that you can never get to a point where you can never have an optimal solution in the game. So that's the idea here. So let's move on to um how to find. So let's say finding Nash equilibrium in simple games. Okay. So to identify Nash equilibrium, follow these steps. Number one, list all strategies. So in this case, you identify all possible strategies for each player. That's the first step. And the second thing is to determine payoffs associated with this strategy, I believe. Determine payoffs. So here you construct a payoff matrix for all strategy combinations. Okay. Then three, you check for best responses. Check for best responses. So that means you need to identify the best response for each player to the strategies of the other players. So if a player makes a particular move, what would be the best response the other player can make? That's how to check for best responses. Then finally, you find mutual best responses. Find mutual best responses. So in this case, a Nash equilibrium occurs when the strategies are mutual best responses. Okay. Now, can we look at a worked example of Nash equilibrium? So worked example of Nash equilibrium. As usual, we have our go-to game, which is the prisoner's dilemma. So we've been working with that a lot. So again, we do that here. So let's look at the game setup start with. Game setup. Of course, again, we are looking at the prisoner's dilemma. We had considered that a bit. I mean, we've been mentioning it all the way, in fact. So prisoner's dilemma. So here again, you have two players. Two players. That's prisoner A, or just call that player A, and prisoner B or player B, right? Player B. So two players, player A and player B, must independently choose. They must independently choose to either cooperate, that is C, or defect, that is D. Their payoffs are as follows. Okay, so you have player A. You have player A here. Player A can either like I'm trying to look for a nice way to do this. I think I've done this before. So you have player A and you have player B. Straight this way. So player B can decide to cooperate. That is C. Or player B can defect. That is D. In the same way, player A down here now. So player B is this way. So player A can also choose to cooperate. That is C. And player B can choose to defect also. And that is D. So, like you can see already, right, that when it comes to prisoner's dilemma, you can actually define the payoffs anyhow you like. But the only thing is that there's a regular pattern to this thing. The regular pattern is that uh you know, for mutual cooperation, they seem to get the I mean, for mutual defection, right? They seem to get the worst, they seem to get the best rather in whatever situation you set up, right? So player B this way and player A this way. Or probably maybe there's even a better way to do it. Maybe if I have an opportunity to do it again, I have a nice way a better way to represent it. But let's go. Or should I do that now? Okay. Okay, I think I just want to do that now. Sorry. Let me just go for that right now. Just got that idea. I think it's a better way of representing this um the payoff table, right? So I think it's more compact. So what we are going to do is we have this and we have this. Then I can just cut this off. So this is player A. I mean, this is player B and this is player A. Yeah, I think this is more compact. And then we can have, so player A can cooperate. That's a C. And player A can defect. That is D. Okay. Then player B can also cooperate. Player B can cooperate, that is C. And player B can defect, that is D. All right. Yeah, I think this is a more compact way of representing this. So, so for when both of them cooperate, so let's say they both get 3 points each. When they both defect, they both get 1 point each. I think the best situation is usually when they both cooperate. Then when uh when B defects and C cooperates and A cooperates, so it's more like B is snitching on A. In that case, B gets 5 points. Then the same thing happens if player A betrays player B. So player A gets 5 points and player B gets nothing. So like that. So this is the payoff table for that. So can we now, our goal here is to find the Nash equilibrium. So which of these payoffs is actually the best? Is the Nash that is the optimal result? So let's go for that. Um, so let's look at a step-by-step solution. In this case, step-by-step solution. So first thing is we list strategies and payoffs. List strategies and payoffs. That's part of what we learned previously. So here we see that if both players choose to cooperate, they each receive 3 points. So that's where we have 3-3, right? So that is 3-3. If they both choose to cooperate, they receive 3 points. Then 2, if both play, if both, if player A, sorry, if player A, yeah, if player A cooperates and player B defects, player A gets 0 points and player B gets 5 points, just like we've seen above already. So vice versa. Okay. Then we also have the third situation. If they both defect, if they both defect, if they both defect, you see that's where they get the least payoffs. So if they both defect, choosing D, right? They each receive 1 point. They each receive 1 point. That's the situation where we have 1, 1. Here it's what you have either 0, 5 or 5, 0. Okay. Now we have listed all possible payoffs. Let's go for next thing now. Number 2, we want to identify best responses for each player. So here, if player B cooperates, that is player B chooses C, then and player okay. If player B cooperates, right? What's the best thing player A can do? So player A's best response is to defect because 5 is greater than 3. See why? If player A cooperates, imagine if player A cooperates, right? That is, so these are the possible solutions. If player A cooperates, these are the possible solutions. But if what I was saying, if player B cooperates, I think that's not what I mean. If player B cooperates, yeah, this is player B cooperating. Okay. And this is also player B. This is player B cooperating. Yeah, sorry, I was correct. So this is player B cooperating right here. So if player B cooperates, these are the two possibilities, right? If player B cooperates, we have so the focus is on player B here. So if player B cooperates, player B automatically gets, we don't care about, we are not interested in what player B gets now because it's settled. So you now see the options available to player A would either be to also cooperate and get 3 points or defect and get 5 points. But player B would, player A would want to get the maximum points possible, which is 5. So the best thing player A can do is to defect so as to get 5 points. So again, I'm trying to explain that if player B cooperates, right? So this is the region. These are the possibilities if player B cooperates. So these are the possible results for player B to cooperate. So if player B cooperates, right? That's settled. But we now want to see what is the best option for player A if player B cooperates. So you see the possible payoffs for player A if player B cooperates is either 3 or 5. And player A wants the biggest possible payoff. And in that case, the best bet is to get 5. And to get 5, player A has to defect. Okay? That's what we are saying here. So if player B cooperates, player A's best response is to defect because 5 is greater than 3. So player A would defect so as to get 5 points. So that goes. Then next, if player B defects, meaning player B chooses D, right? So in that case, player B's defection is so now I guess it's better to erase all this. Okay. All right. Now, if player B defects now, this is the defection of player B. Everything, these are the possibilities if player B defects. Okay. So what will be the best response for player A? In that case, let's look at the payoffs for player A. The payoff for player A is either 0 or 1. And player A would want something as big as possible, right? So it would be nice that if player B defects, the best strategy for player A is also to defect so as to get 1 instead of getting 0. So that's the point there. So if player B defects now, um player A's player A's best response is to also defect. Is to also defect. And the reason because of that for that is that 1 is greater than 0. So player A gets 1 if player A defects instead of getting 0 for not defecting. So that's the second possibility right there. Then number 3 now, similarly for player B, defecting is the best response. Defecting is the best response regardless of player A's choice. Player A's choice. Okay. Now, what that simply means is this. What we did for player B, what if we consider, so let's now do the same thing we did for player A. Can we do it for player B and see what happens? Imagine, for instance, that player A now cooperates. If player A cooperates, right? So the payoffs for player B will be 3 or 5. So in that case, it means that player B also needs to defect so as to get 5 instead of 3. So player B also needs to defect so as to get something higher. So defection is the best thing player B can do, even when player A cooperates. So what if we also consider that player B, okay, what again can we also say? If player A defects, so the same thing happens, right? If player B defects, so the possible payoffs for player A would be, if player A defects, the possible payoffs for player B will be 0 and 1. So player B would rather still defect and get 1 instead of 0. So at the end of the day, whatever happens, for each of them, the best response is to defect. The best response is always to defect. So now that we have seen that, you discover that defect is the best solution. So since we have seen that, now we can now go ahead and go and determine the Nash equilibrium. We have seen that already from all we have done, that defection is the best bet for each of them in whatever situation. So we now determine Nash equilibrium, which is our goal from the beginning. Determine Nash equilibrium. Okay. And how do we do that? We want to determine the Nash equilibrium, which we have found interestingly. So the Nash equilibrium is where both players defect. That is defect for each of them, because neither can improve their payoff by unilaterally changing their strategy. Okay. All right. So for example, if player A switches to cooperate while player B plays D, player A switches to cooperate while player B plays defect. So in that case, now we see that player A's payoff drops from 1 to 0, just like what we saw before. It drops from 1 to 0. So in that case, we conclude that the Nash equilibrium in this situation is DD. Nash equilibrium is DD with payoffs 1, comma 1. That's the best. That's the Nash equilibrium in that situation. Okay, so can we see applications? Maybe some applications of this thing we have just done now. Uh, okay. So now we are done with the worked example, right? So let's talk about some examples and applications of Nash equilibrium. Okay. Examples and applications. In this case, now we have just one equilibrium. Okay. Just like we already learned, we can have more than one, and we may not have any Nash equilibrium. So it's very possible. Examples and applications of Nash equilibrium. Okay. So first of all, the examples. So we have coordination games. Coordination games. So here you have players. Players choose strategies to achieve mutual benefit. To achieve mutual benefit. E.g., driving on the same side, driving on the same side of the road. You know, if they drive on opposite sides, they have to be more careful. They are more prone to accidents and things like that. So, in that case, the Nash equilibrium is to drive on the same side of the road. So it's easy to overtake without having head-on collision with any car. So we also have competitive markets. Competitive markets. So here, uh, firms setting prices, firms setting prices that maximize profits given competitors' prices, given competitors' prices. So in that case, everything is coordinated. So now let's talk about some applications now. Applications. So talking about applications, just like we've seen before, um, we have applications in economics. I mean, in the previous video, I think we made mention of things like this. So we have economics, uh, like in pricing strategies. We have pricing strategies. We have auctions, auctions, and of course, oligopolistic competition, oligopolistic competition. So we have Nash equilibrium applicable in these areas. Then we also have politics, right? Politics. So we have, in this case, we talk about election strategies and international treaties. So countries reach places where they get the best and not better than that. Okay. So election strategies and international treaties. Then we also have that going on in biology. Biology. So here we have evolutionary strategies. In fact, there's something called evolutionary game theory. We're going to see that as we progress. So we have evolutionary strategies in ecosystems. So like e.g., we have the predator-prey dynamics, predator-prey dynamics. So over time, the predator and prey can find a way of coexisting and they reach their Nash equilibrium where, none of them can have any undue advantage over the other. So they play the game and then they reach some kind of stability. All right. So in conclusion, right? Conclusion, by understanding and identifying Nash equilibria, Nash equilibria, decision makers can predict, decision makers can predict stable outcomes in strategic interactions and optimize their strategies accordingly. Okay. So, I mean, you can know the absolute possible way to go about a particular situation using Nash equilibrium. So, as far as you can list out, all the players involved, all the strategies available to the players, and you also know the payoffs attached to the strategies. Then, if you can list all of them and look at the best option for each side, and then you can decide the Nash equilibrium. And this is really useful in practical things, in our world. More things to come after now. We are going to see, I think after now, we'll be looking at mixed strategy Nash equilibrium, and that will extend into like 3 videos or something. So you don't want to miss that. So because of that, you want to subscribe to this channel right away and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you want me to teach a topic or solve a problem, and like and share so that more people can have access to this great content. Till I come your way again, keep playing the games of life with wisdom. Bye.